My name is Chris Matthews and I'm Associate Director here at Atelier One. Now, over the 30 years of our history, we have been lucky enough to try out lots of new ideas. And previously, we've done a lot of work in timber. So in 2001, we did the Earth Center Canopy. This was effectively a form-found space frame structure. We had flitch plate nodes that were all different angles. It was, at the time, the largest solar canopy in Europe. We were early adopters of CLT. This is Kent House. We didn't use CLT for the sake of it, but because it was the best material for the job. At the time, there was an issue on this site that because it was so isolated, people were running away with the tools. So what we needed was something that could be built extremely quickly so that everything could be encapsulated and the sites could be secured. And so that's why we opted for CLT for that particular project. And we've been working in CLT ever since. The Hook Park, big shed. We greatly enjoyed working on that. The unique thing about that is that it's timber in the round. And I mentioned the flitch plate connectors earlier. What we looked at for Hook Park was using simple screwed connections to remove all of that steelwork. And probably our most ambitious timber project was the UK Pavilion over at the Dubai Expo. This was a series of timber cassettes that were all stacked on top of each other. So over the years, we've developed an expertise in timber, and yet right now we have 5 people working in bamboo. And so what I wanted to do tonight was basically explain that journey and then talk about our most successful embodiment of bamboo to date. So the story all starts with Mark Fisher of Stewfish suggesting to Neil Thomas, our founding director, that he visited John Hardy, the founder of the Green School out in Bali. The Green School really is spectacular. Nobody who's been there has ever not come back wanting to build in bamboo. This is their heart of school building. You can see it's post and beam construction, but it really does show the scale and the feel that you can get from bamboo structures. This is their auditorium, the Sankep Auditorium. I don't know about you, but I would have loved to go to school in a structure like this. But out there around the school, there are also various other bamboo structures that have gone up. So this is the house Sharma Springs. That's an elevation view of the same house. So Neil went out there and was amazed. He's an extremely creative engineer, and his mind was full of ideas about how bamboo could be utilized. But what we really needed to do was understand the material first. And so he came back to the UK and he set us to work putting together our own in-house technical design guide for bamboo. I've got to admit, this was about 10 years ago now. I was a skeptic. I saw bamboo and I thought, oh, well, garden structures, why would we be looking at that? And yet, as I got more and more into it, I realized that the properties of bamboo really are remarkable. You can see that this slice through a microscope image with the vascular bundles on the outside exactly where you would want them for a structurally optimal material. The nodes add double curvature to the columns to stop them buckling. But most of all, and to put it very simply, C24 timber, 24 newtons per square millimeter bending strength, and would take about 30 years to grow. This is on the right here, samples of bamboo grown in Shropshire, would take 3 years to grow, and we had it tested in Coventry University, characteristic bending strengths of about 92 newtons per square millimeter. So it is grown in 1/10 of the time, and it's potentially 3 times stronger. But it doesn't stop there. At the moment, with the climate emergency, there is a lot of focus on not just reducing carbon, but starting to sequester carbon. I've deliberately put the articles here rather than giving specific numbers because I think more research is needed into this topic. But at the top here, you can see a Chinese study that shows a fir forest versus Moso bamboo, and you can see that over 60 years, the sequestration for Moso bamboo is about 1.5 times higher. But also the bending strengths you're getting from that Moso bamboo are at least double. There's another study down here which is suggesting that bamboo can sequester per hectare per year 6 times what a timber forest can sequester. These figures need more looking into, but I think they're exciting. I think we have to start looking at bamboo seriously. The argument doesn't stop there. So this is a paper that was written to look at the temperature change per kilogram of particular materials that are grown. Now, I looked at this and thought, wait a second, this doesn't make sense. Let me just flag at the top of this graph that there's a 1 times 10 to the minus 15. So the amount that each kilogram contributes to the total climate change in temperature is quite small. But what you can see is that with bamboo and straw, much faster growing materials, the impact that they can have in terms of temperature change happens much sooner. So with timber, if we started planting more sustainable forests now, then we could have an impact in maybe 30, 40 years. Whereas with bamboo, we could have an impact in 10 to 15 years, which we really need to do if we're going to reverse the temperature increase. I think the other thing to flag is that, yes, there are sustainable forests at the moment, but the majority of those resources are currently allocated. I would point you at this point, if you're looking for further sources, to the work of Will Hawkins over at the University of Bath. The benefits don't stop there. So in terms of environmental benefits, you can use bamboo to restore degraded and polluted soils. You don't have to use prime soil at all. It can grow in really quite poor soil. It also offers shade, shelter, and food to species of flora and fauna. It prevents erosion and surface soil runoff, and the use of fertilizers required is minimal. But there are also socio-economic benefits. So looking at the broader picture of sustainability rather than just environmentally. So you get a significantly faster return on capital. You plant the bamboo, you are getting useful bamboo that can be used for structures within 8 years. And after that, every 3 years, you can harvest the bamboo. And what's great is actually the more you harvest the bamboo, the more bamboo grows in a particular site. So it actually likes being harvested, likes being cultivated. The process of silviculture is extremely simple. It's inexpensive and simple to harvest. So local people can do it. You don't need complex machinery. You can have continuous harvesting cycles. You can harvest some of the bamboo each year. And there is therefore a lot more potential for the farmers to keep more of the added value. If you, again, I'm giving references so that people can look at further sources and all this, but I would thoroughly recommend listening to Arif Rabik and the 1,000 Villages project if you want to see the amazing socioeconomic benefits that bamboo can have. So, sorry, one sec. There we go. Brilliant. So bamboo, it's not a new material. It's been around for thousands of years. There are examples from about 1,500 years ago of bamboo suspension bridges. And everybody I mentioned bamboo to mentions Hong Kong and the scaffolding out there. Yes, the amazing work in Hong Kong where they are building extremely tall scaffolding towers out of bamboo, but we believe it's worth so much more than that. And the limit up until recently has been the long-term durability. Now, Linda Garland out in Bali pioneered a treatment, boric acid or borax, which effectively removes the sugars from the bamboo culms. And it means that they are less prone to insect attack and fungal attack. And it basically allows you to durably use bamboo indefinitely if you treat it right. and we will, or if you use it in the right way, and we'll talk more about that later. So I mentioned that we did our study. We spent about 3 years trying to really get to grips with the material before we even started doing any engineering of projects. We realized that there was a huge amount to learn, and we wanted to get it right. This is one of the very first houses that we helped the team out in Bali with. So we're now working with Ibuku, the architecture practice. And this was one of their buildings, the Crescent Moon House. And it was one of the first times that they actually started to use form-active structures. So the Heart of School building, although very impressive, was using the bamboo as post and beam. And we wanted to start pushing what was possible. So this is a form-active grid shell structure. One of the first ones we contributed to. This is the Bamboo U Hall. This is a model of it. It's a series of high pars, again, using the form to activate or to work structurally efficiently by activating the surface. Quite some space to work in, I have to say. But tonight, I want to talk mainly about the ARC. We believe this is the most successful implementation of the learning to date. So the concept was devised by Jorg Stam, Elora Hardy of Ibuku, and Atelier One, in particular, Neil Thomas. What we love about this is it's a collaborative approach between an engineer, a builder, and a designer. They sat down and they said, what is bamboo good for? What is the best possible form to build with bamboo? What can you only do in bamboo? And this is what they came up with. So it's a series of arches with a series of saddle surfaces between them. So I mentioned that you've got to use bamboo in the right way. It's extremely important that you don't have contact with the ground, you don't have contact with water, and you don't have direct sunlight. And this design encapsulates that ethos. Here it is. So the structure that they devised is 40 meters long, 19 meters across, 14 meters high. And now started a series of testing. The structure or a lot of bamboo was being used, but nobody had really pushed it and seen how far we could take it. So the first point was taking the dendrocalamus asper that's used out there and getting proper accurate data for the bending capacity. So this is a 140 mil diameter column, 6.6 kilonewton meter bending capacity. We did a series of bending tests to really carry out mechanical characterization of the columns that they had. We did both mechanical and geometric, so measuring the diameter and the thickness. It's extremely important, and we'll touch on this later, but for each species, you really do need to get those two things mastered right at the beginning of the project. I showed the curved forms, and how they've traditionally done that out in Bali is a technique called reb-reb. And what you effectively do is you notch one half of the culm and then bend it back on itself. So you have full-length fibers for half the culm, and the other half of the culm, you have interrupted fibers that are pushing on themselves. We needed to get to the bottom of how much that weakened the capacity of the bamboo. So again, we did load testing. So at the top here, you can see a bundle of columns that are jointed together. And then because of the reb-reb, we had to stitch back together the columns on the lower face. And you can see that when there wasn't any reb-reb, on the right here, we had, for a 4-column bundle, capacities of about 44 kilonewton meters. And when we had the reb-reb with the best fixing that we could devise, we tried various different measures to refix the bamboo. We were getting bending capacities of about 14.7 kilonewton meters when the reb-reb face was in tension, and 24.4 when the reb-reb face was in compression. Here's another example of the testing that was carried out. So real large-scale proper testing. It was completely essential. Without doing this testing, we wouldn't have been able to say how much composite action we were getting on the columns or within the column bundles. So we had to test it as an assembly. I showed you that surface very briefly, and that surface is a series of bamboo splits that are connected to the arches, and a material we call plu covering that. So again, we had to load test it. We did a series of tension tests to make sure that we accurately knew the connection capacity and the splitting capacity. At this point, I think I need to give a big shout out to James Wolfe, who coordinated this huge array of testing on site. And so once we had this initial data, we then started running this through our analysis models and looking at how the form was actually working. And what we found was that if you just looked at the arches, there wasn't sufficient bending capacity. If you looked at just the surface, there wasn't sufficient strength in the surface. And so what we ended up doing was demonstrating that actually by using the form of the surfaces between the saddles and using that increased structural depth, that was how you could demonstrate the true strength of the structure. On the right here, you can see this plu surface. So it's basically crushed bamboo laid in both directions, and that gives you an incredibly stiff surface. So to not use that would have been a real waste. Then, because we were now using the surface, we had to test the surface. So this is a full-scale mock-up of one of the leaves of the structure. This is the dead load test, and then this is the wind load test. So where we were trying to simulate what a wind load, what an asymmetric load would do to one of these saddles. We matched this up with our analysis models, and were able to get a feel for how stiff the kind of combined assembly was compared with the predicted models that we had in robot structure analysis. And we were getting a kind of loss of stiffness due to the connections of about a factor of 1.5 to 2. So we were able to use that factor to then feed back into our model to make sure we weren't taking unrealistically high stiffnesses. So here's the arc under construction. You can see the net of bamboo splits there and the arches. And here is the complete form. We're incredibly pleased with how people have reacted to this building. I think it really does embody the kind of biophilic principles that we were trying to reflect. This is the internal view. And so key lessons that we found from the arc. First of all, actually I should have mentioned this previously, but reuse of the existing foundations. There was a previous structure on the site, a previous gymnasium structure that we were replacing. And so there were already foundations there. So the whole thing was designed to reuse those foundations. We spanned the arches from existing support points. We utilized the local skill set. And to be quite frank, the building would not have been possible without the huge skill of PT Bamboo and the local bamboo craftspeople. And it really has been a two-way information exchange with the team out there for many, many years now. I mentioned that before we even started engineering any of these structures, we were looking at bamboo for about 3 years. And it really is a close relationship that we're extremely happy with. Carbon, embodied carbon and sequestered carbon now. So what's wonderful is all the materials were grown locally and harvested locally. Minimal treatment was required. I showed you the only treatment that you have to do, the borax solution. All of the building fabric is acting structurally. We made use of everything. And the form was chosen to suit the material properties. And it's no wonder then that actually the carbon per square meter comes out at 8 kilograms per square meter of CO2 equivalent. If you don't take into account sequestering, and if you do, you're down at minus 14. So we always list both figures. But it really does show that by using these kind of techniques, you can get an incredibly low carbon building. And very pleasingly, with the iStruct embodied carbon calculator, we were able to get a score of A++. So we're delighted with that. And when the structural awards came around, the thing that we were really pleased with was this particular citation. The project demonstrates the exciting possibility of bamboo as a potential mainstream building material. Architects and engineers alike should be inspired. And when Neil was out there 10 years ago, that is what he said. He said, bamboo has huge potential. And so to see the iStruct give us this platform to show bamboo and to acknowledge that potential is hugely exciting for us. And we'd like to thank the iStruct Awards judging panel for acknowledging it, basically, and taking the time to understand the project. Now, the story doesn't end there. So yes, bamboo whole culm is fantastic, but there are other possibilities. So just like glulam and LVL, you can have solid laminated bamboo. You can have strand woven bamboo, and there are even composite panel systems being developed now. So Bamcor over in the States, in particular, are pioneering this. Properties of laminated bamboo. These are taken from Moso. So they are typically getting flexural strengths of about 40 up to 90 megapascals. So compared to C24 timber, which where I imagine lots of people know as 24, you are getting a huge improvement. And we think that actually with different species of bamboo, you can get even higher than that. So what applications is it great for? Well, low rise, you're not generally utilizing, let me restart that. So basically, wherever timber is currently used, there's potential to use bamboo. Low rise, you're not generally relying on strength or not being governed by strength. So it can be used there, but it comes into its own when you start looking at large span structures like domes, like roof trusses over warehouses, and also multi-story construction. And it's happening. The Chinese are doing it. So this is an example of a residential building in the Nanjing Forest University out in China. This is a visitor center also in Nanjing in China. And this is the Norwegian pavilion at the Shanghai Expo. So people are doing it. It's in very early days, but it has been demonstrated to be possible. And the codes are starting to come online. I'll give you a few references right now. So the iStruct have done a brilliant set of papers on structural use of bamboo. Then ISO 22156 has just been updated, which goes into the structural design of bamboo. So the actual design equations, material factors, partial factors, etc., that should be used. There's also ISO 22157, which explains how you do the testing and both geometric and mechanical characterization of bamboo culms. And ISO 23478, which is for engineered bamboo, and that goes into the test methods. There isn't yet a ISO for engineering design of engineered bamboo, but that is something that is being worked on. And what I'm delighted about, all of these 4 documents, David Trujillo was very much involved in creating all of those. And I'm very pleased to say that he is now working with us part-time as our head of natural materials. And it's been absolutely brilliant because having written all of these codes, he wanted to now start applying them and start seeing how these codes could be used. And so we now get the pleasure of a kind of weekly conversation with the guy who wrote the codes to say, what about this bit? What about that bit? How do you apply this? How do you apply that? So it's a great pleasure to have David on board alongside his work at Coventry University. And we're really excited about where that's taking us. So ongoing, what's next? Well, we have active projects in Bali, Costa Rica, Mexico, and the Philippines, all whole culm bamboo construction, which are really looking at how you can build dome construction and different typologies. Laminated bamboo. We are very keen to explore it, and we have a number of partners who are looking into doing this just because of the range of options that it opens up. So one of those is BKVV. They are a Dutch architectural company who are looking or have been given funding by the Dutch government to develop capacity for laminated bamboo in Uganda. UBC, University of British Columbia over in Canada, and a developer called Bamboo Nations are also looking at starting to produce laminated bamboo. And I mentioned a reef earlier, a reef rabbit and Indo bamboo, again, starting to look at how bamboo or laminated bamboo can be used structurally. So that's hugely exciting. I've mentioned geometric and mechanical characterization a few times now. You can't get away from it. Every bamboo project you need to carry out this process for different species, for different plantations, it has to be done. You have to see what material you're working with. And that's something that David is leading on from our side. So we are busy writing specifications for how you go about doing this, and how you can then, once you've got these, or once you've carried out this characterization, how you can then grade the bamboo so that you don't have to reject a whole load of bamboo. You can use all of the columns you have just in different places. And the other one that we're looking at, and we've done a lot of research into this over the last few months, is how we can curve bamboo without using that reb technique. So for the sharp-eyed amongst you, you'll see that the reb technique, the notching of one side of the bamboo, really does reduce the capacity quite significantly. And so what we wanted to do was see if there was a way that we could manage to get these amazing curves without using that technique. Now, a lot of people ask, can we do this in the UK? Is it relevant? This photo on the left here is Treba Gardens down in Cornwall. They are growing a huge range of bamboos up to about, I believe, 12 centimetre diameter. So yes, it is perfectly possible to grow bamboo in the UK. This diagram in the middle shows the hardiness zones across the UK. So you can see that Cornwall and Ireland are the best. You're probably not going to manage to keep bamboo growing in northern Scotland, and that's due to the extreme temperature drops you get in the winter. Interestingly, there's actually a highlight in London because the temperatures don't drop as much, so it's more suitable to grow bamboo in London than the surrounding area. And on the right here, this was a real breakthrough moment for us. So working with Imagineer, or it is as, we were starting to look at how bamboo could be developed and explored in the UK under a scheme they called Bridge to Bamboo. They got funding as part of the Birmingham Cultural Festival linked to the Commonwealth Games. But what they said is, well, okay, we love bamboo. Neil had explained the amazing properties, and they were all accepting immediately that, yes, we had to explore the use of bamboo. But they said, please, can we find a source in the UK? And the breakthrough moment was finding Michael Brisbane in Shropshire, who had been growing bamboo for a really quite long period and had enough bamboo for us to hold an entire festival. So this is Bridge to Bamboo Imagine Bamboo as part of the Bridge to Bamboo program in Birmingham, central Birmingham. We brought bamboo. This is a team of people trying out a high-pass surface. And this was the main structure that we built as part of that festival. So the brief from Orit and the Imagineer team was to demonstrate that bamboo could be used structurally. And we came up with this concept, a spatial frame truss, using the bamboo that was grown in Shropshire. It spanned 14 meters, was 6 meter high, and it was built in 3 days by a team of people with craft skills, but hadn't really worked with bamboo before. It was an experiment. It was great fun. There are a few characters here that were around who joined us. So we've got people from Bamboo U in Bali. We've got John Hardy, the founder of the Green School there. We've got Jed Long from Cave Urban in Australia. And David Trujillo is here. Huge number of bamboo researchers, all focused on Birmingham for that weekend. It was really quite exciting. But the arch, although it could take load, we weren't quite happy. And so it was taken down. The bamboo was stored. Here's a little video of it coming down. There we go. I love that. I love that video. There's a reason, which is that you can really see how flexible that structure is. Because of the temporary nature of it, and because we were using volunteers, we were trying to do everything with lashed joints. But you can see that you do get a really quite flexible structure. So thanks to Appetite, we were given a chance to rebuild the bamboo arch at Keele University in March. So not as sunny, you can see the mud, but we were able to do some testing in advance and really hone in on what needed to happen with the joints. We used mechanical connectors, so 4mm diameter bolts rather than lashing. And the result was that we had a much, much stiffer arch, and we were actually able to have full acrobatics on it. So this is a cloud swinger performing on the Keele arch. And here we go. This is it coming down. And you can see that the different jointing mechanism makes it so much stiffer, and you can actually hear the difference in how it crashes to the ground. So I've spoken and I've covered a huge kind of range of bamboo topics, but I think the most exciting thing is that as a result of the work that Imagineer have been doing and various spin-out schemes, a series of talks called Taking Root was funded and led by Ling Tan. School children around the country, and particularly around the West Midlands, have been learning about the amazing properties of bamboo and have been planting their own bamboo. We're delighted about this. It really does embody what we hoped to achieve, which was showing people that bamboo has a place in the solution that structural engineers need to put forward to fight climate change and reach net zero for our buildings. So there we go. That is where I'm going to finish for today. I'm going to hand back to Will, and then I'm looking forward to all your questions.
Thank you, David. And you're just going to have to imagine the round of applause and the whooping and cheering that's happening right now amongst our audience. But I assure you that it's there. Would you mind maybe turn off the screen share and turn on your camera, because then everyone can see who's been telling them all of this inspirational stuff for the past half an hour. So thank you, Chris, for taking us through that. It was really quite inspirational. And actually, those images of your arch at the end maybe reimagine Wembley Stadium in a whole new light.
I've got to confess, it was based on the Wembley arch. We were trying to recreate that. So there we go.
Bamboo in Birmingham rather than steel in North London. Maybe that's where this is going to end up one day. No, amazing stuff, and really, quite sort of brave engineering in a way. I think sort of take something so new and novel and try and push it to the limits of shell structures and form found structures so early on. So really great to see.